Um, my wife's best friend, they went to high school together, but they live outside of Fort Worth. And we went to see them. They have a little girl who is like a year and a half older than Ellis, and Ellis is bigger than her. They have three kids. We went to see them, and we went to what I can only, anybody ever been to Cancun and been to kind of like an all-inclusive sort of thing? Okay, maybe you get something that's in y'all's like spring break price range of everything. Y'all see the underbelly of Cancun. But we went to this place in Texas. It was a ranch, but it was like an all-inclusive for what I would say is like rich white guys. In that way, because like they had like like they do like hunts and you shoot clay pigeons, and they have a rifle range and a pistol range and pickleball and a rock climbing wall and all of this, like you name it, they have like it's like a country club.
Not to ask, did you go to a ranch or a country club?
It's a little bit of both, right? And so my wife's best friend, her husband works for Yokohama Tires, and he's sort of like, I don't know, he's a well-paid concierge, an event planner. Like he schmoozes the big the tire distributors and things. So they have this thing. Anyway, we went and I shot a shotgun for the first time in my entire life at the age of 45. I'm 2 for 2 shooting clay pigeons. I've stopped. I will never do it again. But Ellis got to do a bunch of different things. So she got to shoot a little model rocket and do rock climbing and a whole bunch of stuff. I had a point when I started telling you all that story, and it is completely gone now. And I have no clue what it is. Anyway, I just know that these things existed, like just out in the things. You see horses? I've never seen a horse before, like up close before in my life. So Ellis has ridden a horse. Yeah, I know y'all are like, who is this guy? Right? So I grew up in a not that big town in Arkansas, but I may as well have grown up in New York City or something. In those ways. All right, so we are needing to talk about the sort of second and very bro-ish portion of resistance training. Okay, and so what we're going to get into today, contractile. I can't spell. I think we talked about that. This is what we call contractile protein adaptation. Okay, so we train, you get stronger. One of the big reasons behind that is an increase in motor unit recruitment and firing rate. And so these neural adaptations, they happen really quickly. But the other part is hypertrophy. It's muscles physically getting bigger. Okay. Loosely, we call that a contractile protein adaptation because you're expanding actin or expanding bias. Okay. So if you look at these sorts of things, when we talk about this, the way we measure these things is by measuring something called cross-sectional area. Okay. So a cross-section, imagine that we take your thigh, okay, and we're going to go like horror movie on it. We're just going to cut it sort of right through this way. Okay. And so it looks like that. Okay, that's a cross section. Just sort of one circle. You're looking up through the heel at all of this. There we go. Okay, you've got some muscle. It's going to kind of come in like this. You've got some hamstrings down here, those kinds of things. So what we're going to look at when you see is this cross section getting bigger, is does it go from that right to that? That might be a little ambitious and fairly large, but that's kind of what we're trying to deal with. Okay, that's the contractile protein adaptation. So if we look at things, okay, if I take a muscle biopsy from you guys, I can begin to see turnover or changes in the myosin heavy chain, thing that we use to fiber type stuff. I can begin to see increased turnover within a week or thereabouts if you've done a couple of consecutive bouts of resistance training. Okay, that stuff happens very, very quickly. But this notable, measurable increase takes a month, probably more like 6 to 8 weeks in most people if we have very, very, very high resolution imaging. So we take a DEXA scan, we take an MRI, we take a CT scan, right? We can very accurately see any kind of very, very small changes that are going to be there. But for you guys to see someone and be like, yo, dude's getting big, right? 8 weeks, 10 weeks, 12 weeks to visually be able to see, oh yeah, that muscle's gotten bigger. Okay. So it's a much, much slower process. And because of that, that creates us problems from an exercise adherence, right? Everybody wants to see results immediately. We see strength results immediately, but it takes a while to get bigger muscles. Okay. So this is always a fun question. How big can you get? Anyone guess? How big? If we ask, it's Monday, we go catch a bro doing bench press today. We ask them, how big do they think they're likely to be able to get?
Huge.
Huge, right? It's the Mean Girls quote, right? The limit does not exist in those ways, right? So in actuality, there is a limit, okay? Unless you're taking steroids, there is a limit. With steroids, we don't really know because we can't do research. It's unethical for us to give people steroids in the doses that are likely to induce the largest amounts of hypertrophy, okay? Without steroids, most of you guys are going to be in the 10 or 15 to maybe about 40%, 50% increase in muscle size. Okay. That's quite a bit. Okay. It's quite a bit, but it's also actually not that much. Okay. Actually not that much. A 150-pound person with 15% body fat increases every muscle in their body. Every muscle, which none of us will ever do. Every muscle by 15%, they gain 8 pounds. Okay, 8 pounds. So anybody that tells you I gained 30 pounds of muscle is completely full of shit. Okay. Or what they gained was muscle and connective tissue and fat and all of these things. It's easy to put on that much weight. I say easy. It is possible to put on that much weight. Okay. And it's especially not that difficult in 17, 18, 19, 20-year-old individuals who are still, right, haven't kind of maxed out growth and all of this. But most people are not getting that big, okay? It's very, very affected by genetics, okay? But we don't have a lot of data. If you will look on your slides, I have a histogram again from the same study, the bicep study, where there are almost 600 people showing average increase in muscle size assessed via MRI in those individuals, okay? And if you will look, it's relatively similar between men and women, and the average is about 20%, okay? It's about 20%. So it's pretty good, okay? It's pretty good, but it's not as much as some people might think that it's good, okay? But you will look at all of that. There's some people, they're never going to get bigger. I'm sorry. Y'all can lift all you want. You're never getting bigger, okay? And other people, they're going to get really big, right? And by really big, I mean maybe out into the 50% kind of range on those things, okay? People that are really, really big, they're taking steroids. It's just the way it is. They're taking steroids. I know it's a gross oversimplification and overgeneralization, but that's the real thing, okay? That's the real thing. Take creatine, maybe you get an extra like 3%. You get your protein powder and your protein things, you get your macros right, maybe get an extra 3 to 5% from where your genetic potential is. But that means you could get 20%, now you're getting 23. You're not getting 50 or 70 or something ridiculous just by doing that kind of stuff, okay? All right, so what I want us to kind of get into today, though, is what's the mechanism? How does this happen? Okay. what do we need to do when we lift? And then what are the actual kind of inside your muscle cellular signals? They're going to transmit things that tell the nucleus, hey, make actin, make myosin, let's make our muscles bigger. Okay. So you guys heard about something called anabolism and catabolism. Y'all heard of those words? Okay. So when we talk about muscle, we got to talk about protein and what we call protein turnover. Okay. So there's a word called anabolism and a word called catabolism. Okay. Anabolism means we are making proteins. Okay. Making new proteins. Catabolism means we're breaking down those proteins. So something like resistance training is weirdly both anabolic and catabolic. It leads to an increase in protein breakdown, but then it also leads to a larger increase in protein synthesis. Okay? And so the net effect, what we are looking at for your muscles to get bigger, anabolism has to be larger than catabolism. For your muscles to get smaller and shrink, catabolism has to predominate over anabolism. And so we call this protein balance, or the net protein balance. Okay. In order for muscles to get bigger, your net protein balance needs to be anabolic for weeks on end. Okay. Right now, most of you, if you haven't, or even if you did work out this morning, many of you are catabolic right now. Anybody not eat breakfast? You guys, y'all are really catabolic right now. Okay. Very, very catabolic. Okay. If you resistance train, you get a little bit of catabolism immediately, and then kind of a little bit of a delayed effect, and you get a much larger anabolic effect after those. So to gain muscle, you must make anabolism predominate over catabolism for days and days and days and days on end. Okay. So there's lots of different signals, that control anabolic and catabolic processes. So we need to do something with exercise and to a smaller extent with our diet, which most of you are reasonably okay with, in order to maximize the anabolic signal and minimize the catabolic signal in order to make our muscles grow. Okay, that's how we're going to do all of that. So one bout of resistance training, especially if that one bout is accompanied by a reasonable amount of protein intake. I mean, ideally it's a little bit before, a little bit during, a little bit after, and you match it with some carbohydrates so you can maximize your insulin response and drive everything to the muscle. But as long as you just eat something, eat some protein somewhere around your bout, will drive an increase in anabolism. And that's great. You're up for today. Maybe even a little bit tomorrow. But then if you don't work out again for a week, it's gone. That's not enough to make your muscles grow. So the key thing to make muscles bigger is consistency. Okay? Consistency of I resistance train, I eat some protein, and that drives this kind of acute increase in these anabolic processes. And I have to do that over and over and over again, so I can accrue enough increase in actin and myosin to get visibly or measurably bigger muscles. Okay? Does that make sense? So when I say the single most important thing to have bigger, stronger muscles is you have to go work out consistently, that's why. Okay? It drives the neural adaptations and it keeps them there. But to get bigger muscles, you got to go 2 times, 3 times, 4 times a week, week over week over week, because that anabolic effect of one bout doesn't last that long. And the effect of one bout is not enough to get noticeably bigger muscles. Okay? Okay, so you guys remember protein synthesis from intro to bio or something, right? If I say transcription and translation, you guys know what that means? What is transcription? Who remembers transcription? Uh-oh.
Is transcription, not translated, but, taking the DNA, making it RNA?
Correct. Okay. Transcription is DNA to RNA or DNA to messenger RNA. Okay. You all remember these things? You have these things called genes, right? That's in your DNA. In order to make a protein, I have to tell the nucleus to make the correct messenger RNA that can then go to a ribosome and then assemble the correct amino acids to do all of this. Okay. So what we need to do and what resistance training does is it drives transcription of certain genes. It drives the transcription of the genes that code for actin and myosin and all the things that are going to go on in a sarcomere. Okay. That transcription, those messenger RNA then go to ribosomes where they will grab amino acids, hence the need to eat some level of protein. Okay. Take those amino acids, assemble them correctly to make new actin, to make new myosin, and then that gets sent off and integrated into our sarcomeres. Okay. That's protein synthesis. That's how we do all of this. Okay? So we got to do something with exercise to turn on transcription in the nucleus. So we talked about those sorts of things. So let me show you guys what happens a little bit with everything else. Okay. If you'll go to the slide that has the data from Miller et al., it's gonna say myofibrillar protein FSR. FSR stands for fractional protein synthesis. We can measure in you guys your at rest and then post-exercise we call fractional protein synthesis. This is our best way to measure sort of anabolic and catabolic processes, that flux of protein one way or the other. Okay. Now, to do this, it's pretty hard because we have to run an arterial catheter and a venous catheter, and then we can infuse you with radio-labeled amino acids, and we can watch their appearance and disappear, their appearance in muscle and their disappearance from the bloodstream. Okay. Running arterial catheters, especially in like the femoral artery, wildly dangerous. Okay, wildly dangerous. I watched a cardiologist try to put one in an experiment that we did when I was a grad student in the brachial artery, and one of our grad students' moms, who was the practice participant, like practically bled out in our lab. Cardiologist trying to do it because the cardiologists don't usually set the lines; it's the nurses that do the lines and those kinds of things. Okay, but you got to run an arterial one and then a venous one, so you can measure what goes in and then you can measure what comes out of a particular muscle. Okay, so anybody wants to see something fun, the data that are on there, and most of the data, to be honest, where we do fractional synthesis rates, all comes from one lab at the University of Texas Medical Center at Galveston. They do a big thing there. What you can see is the change in fractional synthesis rate over 24, 48, 72 hours, up to 3 days after a bout of resistance training. Okay. And what you will note is that 6 hours to about 24 hours post, right, it goes up the most, and then it stays elevated for about 3 days afterwards. Okay. So one bout raises protein synthesis rates to there. When you see things, when you buy your protein powder, okay, and it says 300% increase, right, in all of this, that's all based on fractional synthesis rates. Okay. We can show, and it has been shown, that if I feed you a high protein meal, In the absence of doing resistance training, I can make fractional rates go up. They can double in some ways, okay? If I do resistance training and then feed you, it goes up even more, okay? So we can acutely alter fractional rates by these very, very, very large magnitudes. The problem is that what you see after one bout is great, but it does not translate into a 100% increase in muscle mass 8 weeks from now. Does that make sense, guys? So one bout raises this rate a huge amount. Adding protein raises it even more, but the magnitude of the acute change does not translate to the same magnitude of actual muscle accretion over the course of 6, 8, 12, 16 weeks. So you got to be careful, okay? As my wife would say, it's lying with statistics. It's lying with research in those ways. You take something that's a true statement, but you don't provide the entire context on all of those things. What the protein powder stuff is correct, but that's not the whole story, right? It's not the whole story. You're not going to actually get 200% bigger muscles because of all of that, okay? So that's what we see from doing some of those things. But the question then is, how and why is all of that going to happen? We're going to get into that in a minute, okay? The next slide talks about an idea of something called hyperplasia. Hyperplasia is the idea that muscle fibers split. One fiber becomes two, two becomes four, right? So on and so forth. So an early question in studying hypertrophy was, when your muscle gets bigger, are you actually gaining muscle fibers? And that's how your muscle gets bigger. I had 100 fibers, now I have 200, so it's taking up more space. Or is it I have 100, every one of those 100 themselves get bigger, but I still have 100, okay? So hyperplasia is the idea that they split and one becomes two, two becomes four. We don't think in humans that this is very likely to happen, okay? It seems unlikely. It's difficult for us to test, okay? If any of you want to volunteer to let me cut out, say, your bicep entirely, count every fiber, then put it back in, stitch you up, let you heal, then resistance train you, and then cut it out again, and count all of the fibers, we could get a little bit of an idea about what's going on. But you guys can see the problem, right? That no one's going to let us take their bicep out or their quad or whatever muscle it's going to be. So we have some evidence on this from animal models where you can just kill the animal and count things. And the human data is mostly all from cadavers. They take cadavers and they count the fibers in people that have done resistance training, and they count the fibers in people that haven't. And you look at all of that and we kind of just assume like, it doesn't look like there's that much difference. So probably not getting fibers. Okay. In animals, we do see it, especially if you train sort of lower animals, right? Rats, mice, cats, and those kinds of things. And they do this kind of crazy model where they essentially stretch a muscle out. They cut a muscle off, they stretch it out. And so they kind of, their way of inducing hypertrophy is by a stretch. That seems to be kind of a unique way to induce hyperplasia. We don't ever do that in ourselves, and so we don't really think that that's going to be that big of a thing. Okay, so just in case you know, in case anybody asks, take home is you were born with all of the muscle fibers you're ever going to have in your life. Okay, you were born with all of those. They're just really small when you're born. Now, as you grow, those fibers will get bigger and they will get bigger. And we think in some people, one of the genetic determinants of how big your muscles can get may be the total number of muscle fibers that you have. Okay? If you're a person who was born with a high number of very small fibers in a given area, maybe you have a larger potential to increase muscle size than someone that was born with fewer but kind of relatively larger fibers at the start. Okay? It's hard for us to know all of that, but we think that may be one of the things that contributes. Okay. Okay. So the next slide talks about how do they get bigger. So you're increasing protein synthesis. Okay. And as synthesis increases, two things are going to happen. One, a cross section is going to go from here and it's going to start to get a little bit bigger. Okay. As it gets bigger, initially, what happens as we go from there to there is we just get an increase in protein. Okay. Actin, myosin go up. Titin, desmin, vinculin, all the other kind of structural proteins, they all go up. Okay. Then there's going to be some sort of threshold size at which we have to not only increase protein, but then we have to increase nuclei. Remember, muscle fibers are very, very big as cells go to begin with. They have several nuclei. Okay, they have several nuclei. As they grow, the volume inside of that fiber gets bigger. Okay, every nuclei is able to supply protein to a certain particular kind of volume of stuff around it. Okay. Anybody, think about it this way. Anybody live in an apartment or in an old house or something that doesn't necessarily have central heat and air? You have like a window air conditioning unit or something? You're all looking at me like horrified on those things. Okay. I'm gonna go about it this way. Different way. Okay. Think of nuclei as lamps in the room. Okay. If I do a fun thing like this, and I turn all the lights off, okay? And I have, oh, that's not a thing. I can't even see what to turn a light on. Okay? I turn one amount of light on. These lights that are dimmed, okay? This provides a certain amount of light. If the room was smaller, would it be brighter in here? Yeah, it would be, okay? And so as the room gets bigger and bigger, I don't need just these lights. I need more lights still on top of everything. Okay. And so that is how sort of the idea behind, that's the idea behind sort of increasing nuclei. So phase one, as it says on that, phase one increase is only protein. Okay. Cell gets bigger, protein goes up. Once we get to a certain size, we get into phase two. Protein continues to go up, but we also then begin to add nuclei. Okay? To add nuclei. There's a reason we don't see horror movie giant single cell like amoebas that are as big as this room, right? It's a surface area to volume ratio. It's a nuclei to kind of volume ratio. They just can't get very big because they don't have more than one nucleus to be able to supply all the stuff that it needs. Muscles, that's why they can get bigger, is because they have many nuclei. Okay? So keep all of that in mind. That's going to be a phase thing. Do we think that your ability to add nuclei also plays some genetic role in why some people can get bigger muscles than others? Yes. You have more nuclei per area than somebody else, and that fiber can get bigger. Okay. So there may be some other things that are going on there. Okay. Another really used to be a controversial concept is, does your fiber type affect hypertrophy? Do people that have more, especially type 2 fibers, do they have a greater potential to see muscle hypertrophy? Well, when you look at sort of the data from some experiments, you see some really interesting things. Okay, I want to highlight what that is, and then it may mean one of two things, and we're not 100% sure on what it is. So if you look at the data that I have, what I want you guys to see basically is this is a pre to post individual fiber size looking at muscle biopsies. The dark bars are old men, and by old, not me, okay? One of our staff members said, "Oh yes, Chris, you are definitely middle-aged," and I about cried the other day. I mean, it's true, I am, but I still don't like to admit to those things. Um, Old men are in the dark bars, okay? Young women are in gray, young men are in the white bars. Along the bottom, you will see what we see is type 1 fibers, type 2A fibers, type 2X fibers, and then what we're calling hybrid fibers, okay? And so if we look at this, we think resistance training increases the size potentially of all fiber types, okay? Of all fiber types. It also reduces the sheer number of fibers that are 2X's and that are these hybrid fibers that exist between 2A and 2X. Okay, so resistance training shifts fiber type from 2X to 2A, from hybrid fibers to 2A. And it generally leads to hypertrophy of some level in 1s and 2As and any 2X's that you manage to keep. Here's where things get a little weird, though. Okay, here's where they get a little weird. We do tend to see larger or more, a larger percentage of 2A fibers that grow disproportionately to our type 1 fibers. Okay, so in one way of interpreting that, you can say, is there more potential to increase size in 2A and 2X fibers than in type 1? Yes, but the caveat is that we use our type 1 fibers all the time. So they may have already hypertrophied to some extent because you use them over and over and over again all throughout the day. So they may have already be kind of closer to their top end. And that the thing that really drives which fibers are going to get the biggest is it's whichever fibers you don't use very often are the ones that have the largest potential to grow. And so it's a difficult thing for us to test. So what I want you guys to appreciate is all of them have the potential to get bigger and in some circumstances relatively equally bigger, okay? But when you collect data, it tends to be the fibers that have not been used very often that have the greatest potential to grow, and those tend to be type 2, okay? So it's kind of this nuanced answer. Because there's thoughts on like, well, if you look at people, right, that are, let's just say, sprinters, okay? Sprinters. What do sprinters look like compared to distance runners? Muscular, right? Bernie, they're big. 100-meter guys look big, right? Oftentimes and later. They look very muscular in those things. Very type 2. You see distance runners, and they tend to be not that in a lot of instances. Very lean, but not particularly muscular. And so you could try to draw the inference anecdotally, well, that means that people that have type 2 fibers have a greater potential to be big and strong. And I mean, maybe that's going to be the case, but I think we're also dealing with people that are on sort of two separate ends of the continuum that are kind of genetic freak shows one way or the other. Plus, you got to train with resistance training to be able to sprint because you need rapid force production. And it's very, very unadvantageous to be a distance runner and have even the slightest bit of extra weight to have to carry around. As you guys will see in a couple of weeks, the more weight you have to carry around, your VO2 max goes down. That's more weight you got to generate force to be able to move, right? For any of you guys in the distance team, cut weight over the course of the season. Imagine we try to lose 5 pounds in the week before having to go do a big meet. It works. You can maintain strength and things because that's 5 pounds less you got to carry around, right? Your VO2 is necessarily higher from functionally from that standpoint. So we just got to be careful. Okay. All right. So that's what we know about fiber types. All of them can get bigger, but sometimes it looks like the 2s are going to be that way. Okay. The next slide is a big old jumbled mess. Okay. No one freak out. Nobody freak out. You don't have to know all the things that are on it. Okay? You don't have to know everything that's on that slide. That is a probably 10-year-old representation of many of the intracellular signals and pathways that we think contribute to muscular hypertrophy. Okay? I'm sure if we look for a brand new one today, there's going to be even more things that are going to be on.
I'm like when I look at this, I'm looking at troop movements of like a certain war or something.
Yeah, that in many ways is the thing. Okay, what I want you guys to know, the big thing that I want you guys to know, and over the next few slides, there's probably more information on the slides than what I absolutely want you guys to know, and I'll try to point out where I'm like, here's some data, but don't get too wrapped up in all of this, okay? The thing that we need to turn on inside of your cells to drive transcription of the messenger RNA that code for actin myosin is a molecule that is called mTOR. Okay, little m, big T-O-R, mTOR. One of the original people, not the person that discovered it, but one of the earliest things for research on the contribution of mTOR to muscle hypertrophy now works in Oklahoma City at Oklahoma Medical Research Facility. Her name is Sue Bodine. I'll show some data from her in a minute. But mTOR stands for, this is a weird thing. mTOR stands for the mammalian target of, it's an antibiotic called rapamycin. So the M is for mammalian, the T is for target, the O is for of, and the R stands for rapamycin. Okay. They identified mTOR because if you give the antibiotic rapamycin to these cells, it blocks this particular molecule. And if I inject you with rapamycin all the time and I have you work out, your muscles will never get bigger. Okay, we don't usually give rapamycin to people in those ways, but that's what it stands for. It's the mammalian target of rapamycin. This molecule in many ways functions as kind of the hub of where a lot of these intracellular signals are going to be funneled through there. Okay, they're going to be funneled through mTOR. When you turn on mTOR, there's some other downstream processes, but essentially when mTOR gets turned on, that drives protein synthesis. Okay, it drives protein synthesis. It activates something downstream called P70S6 kinase. Kinase puts phosphorylations on things. Lots of intracellular signals exert their influence by adding phosphates to different groups. But turn on mTOR, you get hypertrophy. Resistance training activates mTOR. Eating protein, feeding amino acids, especially the amino acid leucine, seems to activate mTOR. Okay, it activates mTOR. There's a host of different things that will inhibit mTOR and therefore prevent the effects of resistance training from exerting their influence on hypertrophy. Okay, that's what I want you guys to know. If on all of that, you guys will look upstream of there, you look up towards the top on the cell membrane, lots of receptors on the cell membrane, receptors for hormones, testosterone, growth hormone, insulin, something called IGF-1 or insulin-like growth factor 1. Okay, all of these things, when they bind on the cell surface, eventually, very, very often lead to the activation of mTOR. Okay. Anybody ever done the, I think it's 23andMe, the deal where you can look at like sort of your genetic history and it can tell you like where you're from and all of those kinds of things? I think it's 23andMe. One, they keep your data and they've sold your data to it's either Pfizer or Merck or somebody to look at, just not necessarily that terrible of a thing to try to identify things, but I think it's 23andMe that will tell you, do you have a familial risk of cardiovascular disease and type 2 diabetes? They will also tell you, do you have potential to be a better endurance athlete or kind of to gain muscle mass and kind of power and those sorts of things. And what they look at, if you go upstream just a little bit in the middle, there's a molecule called AKT that is there. And that's what it looks for, is AKT. If you have lots of AKT, you turn on AKT, then it eventually activates mTOR and you can get muscle mass. Okay? If you have low levels of AKT, you're likely not going to have the same potential to increase muscle. So these are all the things that we've kind of learned and that we've known. A lot of the stuff that we know about all of these pathways comes from growing muscle cells in a petri dish or from doing things to rats and mice, these animal models of stuff. There's very little of this that we know about from humans, other than we'll take some cells out of your muscle and we'll grow them in a petri dish. Okay. Okay. The next slide talks about kind of traditional anabolic hormones, testosterone, growth hormone, insulin, and insulin-like growth factor. Couple of things that we know about this. Much of what we know about the effects of anabolic hormones, okay, comes from people that don't make enough of that hormone under regular circumstances, okay? We can put estrogen on there too. But there are men that are on the low side of testosterone for their age, okay? Or there are men that are sort of a little bit older than me that we have reached andropause where our testosterone begins to decline, okay? Similarly, we know things about people that are low on the growth hormone, or there may be a pituitary giant and they have very, very high levels of growth hormone. So much of what we know from all of that comes from those things. There's been a couple of studies where they've actually given people testosterone. When you give testosterone by itself, it drives protein synthesis, period. You don't have to work out at all. I inject you with testosterone, sit on your couch, eat hot Cheetos, you get huge, okay? If you take the testosterone and you resistance train, you're gonna get just ginormously huge, okay? Ginormously huge. The extent to which that happens is somewhat dependent upon sort of how far above the normal kind of dose, the normal physiological levels of testosterone you go. We have more data on men that are going through andropause that they give them just a little bit of a boost, just get them back to kind of a normal physiological level that like average 25-year-old guys have, okay? And it prevents decline of muscle. So we know that it's very, very powerful and it has lots of these effects, okay? Growth hormone, similarly, if I give you growth hormone, it drives a little bit of protein synthesis, okay? If I give you growth hormone and you work out, there's not the additive effect with growth hormone. You're going to get bigger from growth hormone, but you're not going to get sort of exponentially bigger with growth hormone plus the working out. There's no kind of additive effect like there is with testosterone. Increasing testosterone levels also drives increases in growth hormones, so it's sometimes difficult to tease out the individualized effects of one versus the other. One of the big consequences of exogenous growth hormone is bones get bigger. Your feet grow, okay? Ladies, wait till you're pregnant, okay? You're gonna need to buy all new shoes, many of you. My wife took full advantage of that. Okay, we redid her entire shoe game, right? Because her feet got like half the size bigger. Hat size, you see skull growth, okay? So that was one of the ways that they knew that a lot of the baseball players in the 90s were all taking growth hormone as their hat size got bigger, okay? So kind of be aware of what those two things are. The last one I want to spend a little bit of time on, because you guys probably haven't heard as much or seen as much about it, is a thing called insulin-like growth factor 1, or IGF-1. Okay? It is generated downstream. So if you increase growth hormone, you will make more IGF-1. Okay? IGF-1 comes primarily from the liver and from skeletal muscle. Okay? It also comes in two distinct flavors. Okay, two variants. There's IGF-1 that comes from the liver. There's an identical variant that comes from the muscle. That's regular IGF-1. Okay. There is also a subvariant that only comes from skeletal muscle. It's the IGF-1 EC variant, but it's oftentimes called the mechano growth factor, or MGF. The interesting thing about IGF-1 and especially MGF is it's very, very powerful at activating satellite cells. Okay? Activating satellite cells. So it's very important for repair of damage to skeletal muscle, and some of those satellite cells will also become new nuclei at some point. Okay? The MGF is what we call an autocrine. You guys know what an autocrine is? There's endocrine, there's paracrine, and there's autocrine. What makes something an endocrine? Endocrine function. Where does it have to go? It's released from a tissue and it goes into this bloodstream, the bloodstream. Okay. Testosterone is endocrine. You release it and it goes into the bloodstream and then it goes to the tissue. Paracrine, it gets released by a tissue and taken up by a tissue immediately adjacent to it, so close to it. Autocrine is it's released by a tissue and it binds right back on that same tissue. Okay. MGF is very much an autocrine. So it's released by skeletal muscle fibers in response to resistance training, and it binds back and signals on those same muscle fibers. If you want to dope using IGF-1 or MGF, you have to inject it directly into skeletal muscle that has just recently contracted. Okay? Just recently contracted because it functions as an autocrine. So exercise does two things. Resistance training tends to do two things. One, it stimulates the release of these hormones. Okay? Stimulates the release of those hormones, but it also stimulates the synthesis of and upregulation into the membrane of those cells of the receptors for all of these hormones. So it's one thing to have more testosterone floating around. It's a whole other one to also now have more testosterone receptors. Okay. This is why we get specificity. Testosterone goes everywhere, but the muscles that just contracted have more receptors for testosterone. So testosterone binds more powerfully in those tissues. This is how we get this idea of specificity. Okay. Okay. So there's some fascinating things about, do people that have more testosterone or more IGF-1 or more growth hormone respond better to resistance training? And the answer is maybe. Okay. People that generally have higher levels of testosterone at baseline, both men and women, tend to have more muscle mass. Okay. They just tend to be, that's where they are. Okay. Those people tend to be better powerlifters and better sprinters and those things, right? Look at female sprinters in swimming, in running, and those kinds of things, right? They have much more, we'll just call it muted secondary sex characteristics, right? Narrower hips in many ways, right? One, that helps them to run faster. Their Q angle is a little bit better. They also tend to be more muscular. Broader shoulders, narrower waist, okay? Consequence of higher testosterone. So there's some data in the next slide There's a really kind of world-renowned lab at the University of Alabama, Birmingham, where they study a lot of those signals that contribute to hypertrophy. These are some data from that particular lab, and they have some evidence that people that have a larger testosterone release, a larger IGF-1 release after a single bout of exercise, do over time tend to respond better to resistance training. Okay. The weird part of this is we know that you have to have some testosterone in order to get a hypertrophic response, right? Having a little bit more is probably a little bit better, but it's not wildly better within kind of normal physiologic things. Same with IGF-1. There is some evidence on all of this. So there's some people that we call responders, non-responders. So potentially one of the genetic things that contributes is just your hormone levels. Okay. But how important can testosterone be truly when percentage-wise, ladies, y'all can get just as big from your starting point as the men, and you all have a tiny fraction of testosterone. Okay. Now, estrogen can be anabolic. There's some other things that are going to be there. So there's a little bit of nuance. Okay. The next slide shows data from satellite cells. Satellite cells are these muscle-specific stem cells that exist in and around your muscle fibers. Okay. They are turned on by IGF-1 and MGF, and they are absolutely key and necessary for repair and growth of muscle fibers following resistance training. Okay. If we take isolated muscle cells from humans, or we take muscle from animal models and we zap them with radiation and we kill the satellite cells, and then we put it through things that would induce hypertrophy, we get basically no hypertrophy. You have to have satellite cells, and they have to be functional in order to do all of this. Okay. We do not fully understand all of the intricacies of this. Okay. They're doing lots of research on it in Oklahoma City at OMRF, but we know that we have to have it. Okay. We know that we have to have them. So that's what the data that I have on there shows, is that if you irradiate the muscle and kill the satellite cells, then they do a thing in animals, they call it synergist ablation. It would basically be me taking you guys and cutting the tendon that goes to both of your gastrocs, and then making you walk around and do things just using your soleus. Okay. Your soleus will get huge, but that's what they do. They have the two, or, take your quad, and I'm going to cut the medialis, and you can't use your medialis, and you got to use your other three knee extensors. So when you cut the synergists, the other synergists are going to be the ones that are going to get overloaded, they're going to grow. Okay. So they irradiate, they do the ablation, this big overload, no increase. They do just the ablation, big increase, right? Or they do just the irradiation and no ablation, and we get nothing. So that's what that data is showing. All it does is it tells us that satellite cells are okay. Don't worry about the next slide. Don't worry about the one that talks about AKT overexpression. Okay. It's on there. I like to mention it because AKT is one of the things that you can see if you do those genetic screenings. Okay. But if we find animals or people that have higher expression of AKT, that leads to more mTOR activation in general, they tend to get bigger muscles. Okay. We can manipulate that in animals and isolated cells. We can block AKT, no hypertrophy, right? We can do some things there, but that's kind of what all is going on. Okay. And then I put the stuff from Subodine on there. Don't worry about what it's saying, but it's basically just the data in the next slide from 2001 from Subodine. Just if you block mTOR by applying rapamycin to the muscle, then you don't get hypertrophy. And that was so they found mTOR, but some of Sue's data was some of the first one to show that if we block it and we do things that should induce hypertrophy, we're not actually going to get it. Okay. Okay. So how does exercise stimulate mTOR? How do we stimulate anything? How does exercise stimulate the increase in testosterone and growth hormone? You guys know what a lot of this is, you get a larger testosterone increase from aerobic training than from resistance training. You get a larger growth hormone increase during aerobic training than during resistance training. Both of those things drive the availability of carbohydrates for fuel use. We're talking about hormonal regulation of blood glucose in a couple of weeks. Okay, so there's got to be something about resistance training specifically that makes these cells receptive or more receptive to the effects of activating mTOR. What we think it is high levels of force applied along the sarcolemma. Okay, when I do a squat and it's very, very heavy, it's very tight in the squat. All right. Oh, yeah. All right. The squat form is really, really bad today. If I do a squat, all right, I'm down like so, and I lift, right? As I'm going down and I'm stretching during that eccentric contraction, I'm loading the muscle. That load is being transmitted along the outside of the sarcolemma, and it kind of, it's like stretching a rubber band. It sort of puts tension on the sarcolemma and it makes it move around like this. Okay, that in and of itself, that stretch and that stress, that disruption on there, seems to be one of the signals that activates mTOR. Okay, we know that stretch is vitally important for preventing muscle atrophy, but it also seems to be somewhat helpful for inducing hypertrophy. Okay, we know that if we put you on bed rest, that whatever muscles are, you're laying in bed, whatever muscles are stretched or more stretched while you're doing that, don't hypertrophy nearly as much as the ones that are short. If we put you in a cast, right, and I cast you with your arm up like this, your bicep is going to shrink, your tricep won't shrink hardly at all, even though both of them are in the cast and they're not doing it. So we think that doing an eccentric movement as part of any resistance training protocol, which if you do a dynamic contraction, almost everybody has to go down and up, right, is important. And there's some evidence, right, that if you do con-ec versus con only, that you get greater hypertrophy. Nobody really trains concentric only anyway, so it's kind of pointless on all of that. But we think that the stretch is important, and we think that load is important, and then we also think that reaching failure, reaching that a metabolic endpoint where there's very high levels of fatiguing metabolites inside of the muscle is also really, really, really important. I got to plug the computer in. Okay. Okay. So, have you guys heard of myostatin? Let's do that the next. If you go on to the next slide, you'll see this giant Belgian blue bull, right? That bull's never lifted a weight a day in its life. And yet it is huge. You want to see something that freaks you out? Google myostatin deficient dog. Okay. Myostatin or mouse or rat, there's myostatin deficient everything. Myostatin is the opposite, let's just say, of testosterone. Okay. Myostatin is a naturally occurring protein, but myostatin limits muscle growth. It limits growth. Okay. And so there are animals and people that have very little to no myostatin, and their muscles can get way bigger than those of us that have normal or elevated levels of myostatin. Okay? So, yeah, the myostatin deficient dog freaks me out. Straight out of like a horror movie or something on all of those kinds of things. Okay? And so there are other proteins that function to limit muscle growth. So if in all of you guys, I give you a supplement that I'm sure exists that blocks all of your myostatin from functioning, it's sort of like giving you steroids. Okay, except your testosterone levels don't actually change and everything else. And maybe there's not the secondary consequences, we'll just say, of all of that. Okay, so that's myostatin. Okay, so in the very, very last sort of thing, okay, and I apologize, I meant to find a paper and some data. I'll look it up and we'll start with it on Wednesday. But what should you do? Okay, we know that we need to do something if we want to get bigger muscles. We got to activate mTOR. We know that something about that comes from loading. Something about that comes from the antibiotic hormone response and from disrupting our membranes. If you're going to go and train today, what should you do? Okay. What do the bros think you should do versus what should you actually do? Okay. And so there has been for the longest time this idea of that you need a certain amount of what we call volume of resistance training. Sets multiplied by reps, multiplied by the amount of weight that you lift, and that you need to overload and do more volume than what you're accustomed to. And that will get you more hypertrophy. Okay? In untrained people, completely untrained people, 1 day a week, 1 set, 10 repetitions, okay, works for about 6 to 8 weeks. Okay? You will get stronger, you will get a little bit worse for about 6 to 8 weeks. After that point, you cease to be completely untrained. So we know to maximize hypertrophy that 2 days a week on a muscle is probably a better stimulus than 1 day in people that are a little bit more trained. There's some evidence that 3 or 4 sets is a little bit better than 1 or 2 sets. Okay. So at some point, more is better, more volume, more days per week is better. Probably because as we become accustomed, that's what we have to have to induce overload that we need to activate input. The fascinating thing now, and I apologize, I'm going to contradict any of you that have had personal training or advanced strength and conditioning. I'm about to say something that contradicts everything that likely is in those books and any kind of test that you're going to take. Okay. So I apologize, but this is what the research tells us. There is no correct or better set and rep range to induce hypertrophy. They all work as long as you lift to what we call failure. I wanted to do 8 reps, I did 8, I tried, I could not do a 9. I wanted to do 30 reps, I did 30, I could not do 31. Okay? Lightweight, heavyweight does not matter. Getting to failure is one of the key things to inducing hypertrophy. There's been multiple studies in the last, say, 5 or 6 years. They do sets of 4, sets of 10 versus sets of 50. If you go to failure, it all is the same. It's all the same. So the idea of a rep range to induce hypertrophy is technically not correct. Okay? It's not correct. We do know if you want to maximize strength, you have to lift high weight, low reps. That will induce hypertrophy, but it also maximizes those neural adaptations. If you lift lightweight, high reps and go to failure, you'll get hypertrophy, but you will not get nearly as strong because you're not training the nervous system to lift very, very heavy. Okay? So it's okay. I don't see this nearly as often as I used to. Okay? But it's okay to have, and I apologize, it's going to seem very sexist, right? That they used to make them, the little pink like dumbbells, right? That weigh like 3 pounds or 5 pounds, okay? You can take those and do curls for as long as you want, okay? It's fine. You'll get hypertrophy as long as you go to failure. Whatever you're doing, you can't do another, okay? That's the problem. It's hard to lift a lightweight all the way to true failure. And so most people will say, let's do something a little bit heavier. We'll help us get there. We're not gonna want to just quit. Okay? So that's the take. A couple of days per week, several sets. Make sure you're going to failure. Sometimes lift relatively heavy, and you're in very, very good shape. Okay? All right, we'll stop here. We will take our quiz over resistance training first thing Wednesday morning. And then we're gonna start the next step. Okay? All right, thanks, guys. See you on Wednesday. I will have your test on Wednesday. I still have not gotten the test from the DRC, so I'm waiting. I'm gonna walk over there today and physically pick them up. So we'll have tests to give back on Wednesday.
Kind of a bro science question. I was over stuff we were talking about today. I've heard a lot of